Good morning, lecturers. This is Andy from IS Team 8. Our team members are Justin, Ka Hui, and Zhihao. Before presenting on our posters, we would like to take this opportunity to thank Defense Science and Technology Agency for allowing us to work with them on this Adversarial Artificial Intelligence in Computer Vision project. Computer vision is a field in AI that enables computers and systems to derive meaningful information from media such as digital images. It will then proceed to make recommendations or decisions based on that meaningful information. However, they are susceptible to adversarial attack, and hence we will be exploring how adversarial AI works and the possible solutions to counter the adversary. This relevant problem statement will be shown at the top left for the audience to have a feel of what the poster is going to be addressing. We immediately showcase the problem for the audience to comprehend by creating a form of comparison in the most simplest way on the top right corner of the poster. From here, you can see that the AI system has shown to be able to be easily fooled by specifically crafted images, also known as adversarial image. These images are carefully manipulated in pixel levels that look like digital noise to the naked eyes as seen in the middle picture. This digital noise is also known as perturbation. To produce these images, adversaries are able to use methods known as evasion attacks that can be seen in the background section. Two of the commonly used evasion attacks are the Jacobian saliency map attack and the fast gradient sign method attack. Although each attack has its own unique way of generating the perturbation, one common characteristic is its property of generating a layer that overlays the input clean image, which are usually too small and not visible to the naked eyes. This whole section will allow the users to understand why adversary attack is of concern in the AI field. Luckily, there are some adversarial defense to counter some of the properties that the evasion attacks have. As seen under adversarial defense section, at the bottom left of the poster, some of the available defense techniques are data preprocessing, runtime detection, and model hardening. Data preprocessing technique is a form of transformative techniques that helps to reduce the adversarial noises when applied to an adversarial image. One example of the technique will be spatial smoothing as seen on the right side of the data preprocessing section. As adversarial pixels tends to be of more distinct characteristics than non-adversarial pixels, the adversarial pixels will be smoothed out when applied with spatial smoothing, which makes the adversarial image look much similar to how the clean image would originally look like. Meanwhile, runtime detection works by extending the model with a detector that is able to help to detect adversarial images right before the classification process. Lastly, model hardening is the concept of applying techniques that improve the robustness of the model against adversarial attacks. This is done so by performing adversarial training using existing tools like Adversarial Robustness Toolbox that is available on GitHub. Lastly, the team created an interesting use case from our experiment, which is the Google CAPTCHA, as seen on the bottom right poster. Our research has realized that Google CAPTCHA utilizes adversarial images in its CAPTCHA as a means to deter and distinguish humans from bots for its authentication process. Thus, the team decided to explore if Google CAPTCHA could be bypassed since it is well protected from bots to determine the content of each image. Through our hard work, the team has managed to retrieve the adversarial image and bypass the CAPTCHA by performing data preprocessing techniques on the adversarial image and sending it for classification through our model that has been applied with model hardening techniques. With our poster, we hope to inspire our fellow juniors in SIT to learn and pursue more in the field of information technology. With that, thank you for listening.